this is the one-dimensional kinematics topic, section 2.3, calculating distance versus calculating displacement for two vectors that are at a right angle to each other. So let's see what we mean by that. We have a young lady named Jasmine, and Jasmine is planning to walk 4.0 meters east and then 6.0 meters north. So Jasmine is going to start right here. We'll label that start. I'm going to put a little dot there so that my measuring is accurate. Since Jasmine is going to walk 4.0 meters east and then she's going to walk 6.0 meters north, my scale on my paper is going to be 1 meter equals 1 decimeter. On your paper, the scale is going to be 1 meter equals 1 centimeter. What you should do right now is pause the video and go get a metric ruler. You could possibly also use a protractor. You need pen and paper, all right, and a calculator. So pause the video and go get those things. All right. We're going to do a scaled diagram, and we're also going to do the math. So there are two ways to figure out the distance and the displacement. All right, one of them is to do a scaled diagram, and the other one is to do the math. Let's start with the scaled diagram. So for 4 meters east, I'm going to draw a vector that is exactly 4 decimeters and to the east. All right, there's my 4 decimeters. So that is actually representing a vector 4.0 meters to the east. Now, remember that to add vectors, we use the tip to tail method. So here's the tip of this vector. All right, we're now going to start the tail of the next vector. And we're just barely going to have enough room here. Here we go. 6. All right. Oops. We want that to be straight. All right, so we've got 6 meters north. 6.0 meters north. Here's the tail. Here's the tip. So that is where we end. This is where we started. This is where we ended. Now, to draw the resultant, or the displacement, we're going to go straight from start to end. All right, here we go. Start to end. There we go. All right, so that's the resultant, or the displacement in this case. Now, the first thing that we're going to do mathematically is calculate the distance that Jasmine walked. Distance is a scalar, so we don't care about direction. We're just going to add up the 2 walks that Jasmine performed. So, we'll use a simple equation, distance total equals d1 plus d2. Jasmine walked 4 meters, and then she walked 6 meters. So the total distance that Jasmine covered, the distance total, is 10 meters. All right, this is the distance that Jasmine covered. Notice that distance has only a magnitude because it's a scalar, and there's the unit. Now we're going to calculate the displacement, Jasmine's displacement, in 2 different ways. We'll do it using the diagram, and then we'll do it using math. Remember, what we are doing is adding the 2 vectors that Jasmine walked. This vector plus this vector. But to add vectors that are at a right angle to each other, ultimately we're going to have to use the Pythagorean theorem. All right, but for now, let's just measure the hypotenuse that we created here. All right, so this hypotenuse is 7.25 is what I've got here. 7.25 decimeters. 7.25 decimeters. So that means that Jasmine's displacement is approximately, what I'm getting here from my diagram, is approximately 7.3 meters. All right, so far that's the displacement, and I hope that the drawing is fairly accurate so that my displacement is fairly accurate. Now, that's the analytical method using a diagram. We're now going to do it mathematically using Pythagorean theorem. All right, here we go. Calculating Jasmine's displacement mathematically. So here's my right triangle. There's my hypotenuse. I'm trying to calculate the hypotenuse. I'm going to call the hypotenuse D for displacement. I'm going to call this leg A, and I'm going to call this leg B. So that the Pythagorean theorem becomes D squared equals A squared plus B squared. If you would prefer to call this C, go ahead and call it C. It doesn't really matter, as long as you label your diagram clearly so that people know what you're trying to calculate. All right, so we have A squared. So A is 4.0 meters. That gets squared. Notice that you must square the number and the unit. The number and the unit go inside the parentheses, so they both get squared. We're going to add to that 6.0 meters squared. All right? So we're going to have 16 plus 36, that's 52. So the displacement squared is going to be 52. So we're going to take the square root of both sides, and we find that the displacement, right, is exactly 7.2 meters. So our mathematical method is very, very close to the analytical method when we actually measured what we drew. Now, if I was a little bit more careful with my drawing, I would have gotten 7.2 instead of 7.25. My drawing is off a tiny little bit. That's almost to be expected, but you really have to try very, very hard to get the drawing accurate. Of course, we trust the math more. The math is inherently more correct than the drawing, where we can make lots of mistakes. Now, we are not quite done with the displacement yet. We need, for a vector such as displacement, we not only need to state the magnitude, we also need to state the direction. And this angle right here is the direction of this vector. You see the arrow up at the top. This angle tells you the direction of that vector. It's not east. Watch. Okay? This vector is north of east. We want to find out how many degrees north of east this vector is. So we'll do some trigonometry to figure out that angle. Now, this is the angle. This vector is adjacent to the angle. This vector is opposite the angle. Now, I do know now that this hypotenuse is 7.2 meters. But I trust the information that I was given, the 4.0 meters east and the 6.0 meters north. I trust that information more than I trust I could have possibly made a mistake in calculating the 7.2. So I'm going to use the adjacent and the opposite. Therefore, I'm going to be using tangent to figure out this angle. Remember, SOHCAHTOA. SOHCAHTOA. In trigonometry, that means the sine is the opposite over the adjacent. The cosine of the angle is the adjacent over the hypotenuse. The tangent of the angle is the opposite over the adjacent. Since we are going to be using opposite and adjacent, we're going to use tangent to figure out that angle. So, tan theta, there's theta, equals the opposite over the adjacent. The opposite over the adjacent. Now, let's start plugging in. The tan of theta, the opposite is 6.0 meters. 6.0 meters. The adjacent is 4.0 meters. I take 6 divided by 4 in my calculator, and I get 1.5. So the tangent of theta is 1.5. Now, I don't want the tangent of theta, I want theta by itself. How do I get rid of tangent? That's right, you take the inverse tan. But whatever you do to one side, you have to do to the other side. So if I take the inverse tan on this side, I have to take the inverse tan on this side as well. Tan and inverse tan cancel, and we get theta equals the inverse tan of 1.5. So, take the inverse tangent. On most of your calculators, it's going to be shift tan. Take the inverse tangent of 1.5, and you find that theta is a 56-degree angle. That angle is 56 degrees, right there. That's a 56-degree angle. So, to state the displacement completely, the magnitude and the direction, right, here we go. The magnitude of this vector right here, all right, is 7.2 meters, right? So the displacement is equal to 7.2 meters. I'll put a comma, and it is 56 degrees. Now, the way you name this, all right, it's going to be of east, it's going to be near, right? North of east, not east, near, right? North of east. 56 degrees north of east. So, you have, for the displacement, you have the magnitude, that's the number with the unit, the magnitude of Jasmine's displacement, and the direction of Jasmine's displacement. The direction in this case is not exactly east or exactly north or exactly south. She is ending up 56 degrees, right, north of east. Now, the only time you would be allowed to say northeast is if she were exactly 45 degrees. If it's a 45-degree angle, you can say northeast or southwest or southeast or whatever. But in all other cases, you're saying north of east or south of east. All right, north or south comes first, and then say of, and either east or west. That's one popular convention which I'm using here. Okay, we're going to move on to another problem that's pretty much similar to this problem, but you need another problem for practice, so here we go. For this problem, we have a young man named Marcus, and Marcus is planning to walk first 8.0 meters south, and then 3.0 meters west. So let's start with a scaled diagram of Marcus's walking plans. So, here we go. 8 meters on my board is going to be 8 decimeters. On your paper is going to be 8 centimeters. So, 8 decimeters. All right, from there to there. All right, Marcus starts here and walks 8 meters, which on my scale diagram here is 8 decimeters. So this is where he starts. That is start. All right, and this is his first vector, 8.0 meters south. Using the tip to tail method, here's the tip of the first vector. We start the tail of the second vector. The second vector is 3 meters west, so I'm going to draw 3 decimeters to the west, right there. It would be nice if it was straight. 3 decimeters to the west. Okay, there we go. All right. So first, 8 meters south, and then 3 meters west. 3 meters west. All right, this is where Marcus ends. All right, now we draw the vector that represents Marcus's displacement, straight from start to end, his change of position. He started here, he ended here. Let's draw that resultant displacement. Oh boy. Wow. Okay, that came out nice. All right. So there's the arrow. His displacement was that way. Okay. Now let's calculate first the distance that Marcus covered. Distance is a scalar. It has only magnitude. We don't care about the direction. So we're just going to add up all of the vectors that Marcus walked. So distance total is going to be d1, we'll make this d1, plus d2. Marcus went 8.0 meters, and then he went another 3.0 meters. So the distance that Marcus covered is a total of 8 plus 3, 11.0 meters. That is the distance that Marcus covered. Now, we want to figure out Marcus's displacement. So, let's first use the diagram to figure out analytically, that means by measuring, what Marcus's displacement was. So from there, right, from there to there, right, I am getting exactly 85, right, 8.5 decimeters. Right, I hope you're getting something like 8.5 centimeters on your drawing. All right, so we've got a displacement of 8.5 meters. All right, this is what we believe the magnitude of the displacement is. Now you could also take your protractor. All right, I tell you what, let me go get a large protractor. I'll be right back. I have my protractor now, and we're going to measure the angle so that we know how many degrees, all right, this vector here is not west, all right, it's south of west, but how many degrees is that there, all right? If I draw a straight line across here, all right, how many degrees south of west is my vector? All right, so let's figure that out. Now, you can measure on your little, with your little protractor, if you have a little plastic protractor, you could measure this angle down here, because this angle right here would be the same as that angle there. All right, this angle here is the same as this angle up here, the one we're looking for. So you could measure this one. All right, if I measure this one right here, all right, I'm getting approximately from here 10, 20, 30, 40, 50, 69 degrees, right, is what I'm getting, okay? Getting 69 degrees. I'll measure this one up here, but I need it to be straight, all right? Okay, so I'm getting about 70 degrees here. So something like 69 or 70 degrees is about right for this angle here. All right? So we've measured the angle. All right? It's about a 69 degree angle. We know that this hypotenuse here is about 8.5 meters. All right, so we're, based upon our analytical drawing, we're getting something like the displacement is 8.5 meters, right? 69 degrees, not west, right? But near, right? South of west. All right? So now let's do the math and see if we get something close to that. All right? Here we go. All right, so we're going to use the Pythagorean theorem to calculate this hypotenuse. We'll call the hypotenuse D. We'll call this leg A. We'll call this leg B. This leg down here was 3.0 meters. This leg was 8.0 meters. Here we go. All right, D squared equals A squared plus B squared. Right, A was 3.0 meters squared. B is 8.0 meters squared. All right, we're getting 9 plus 64. All right, so that's 73. We're going to take, since D squared is 73, we're going to take the square root of both sides and find out that our displacement, the magnitude of our displacement, take the square root of 73 on your calculator, and it rounds to about 8.5. All right, not bad. So that's 8.5 meters. All right, so that matches up with what we have there. All right, now, for our tangent, all right, for our angle here, we're trying to figure out this angle. Let's do the tangent. It's going to be opposite over adjacent. All right. I'm going to grab a calculator. Here we go. So let's do the tangent. Do you want to take a minute to copy that? Do you want to freeze the video and take a minute to copy that? Okay. So if you want to copy that, pause the video and take a minute to copy that right there. Okay. All right, I'm going to erase it. Now let's figure out the angle. This angle here, which is the same as that angle there, that's the angle that we're talking about. Okay? So, the tangent of theta is going to be the opposite over the adjacent. Here's the angle theta. The opposite is 8.0 meters. The adjacent is 3.0 meters, right? Opposite the angle is 8.0 meters. Adjacent to the angle is 3.0 meters. Right, 8 divided by 3. Okay, 2.666. All right, so the tangent of theta is 2.666. All right, but we don't want the tangent of theta. We want theta. How do we get rid of tangent? Take the inverse tan of both sides. The inverse tan of both sides. Tan and inverse tan cancel. I'm left with theta. Theta being the inverse tan of 2.666. So do shift tan, that's inverse tan for most of your calculators, of 2.666. All right, and I'm getting for my angle 69 degrees. Wow. Okay, so this measurement up here, this measurement down here was quite accurate. This one was more like 70, so my drawing wasn't perfect, but this one down here was more like 69. All right? So in other words, everything wasn't exactly square up there. Okay, so theta is 69 degrees. All right, now, let's write out our displacement once and for all. Okay, actually, let's start with the distance and then write out the displacement. If you want to pause the video and copy any of this, do that now. Okay? All right. Now, distance and displacement are not the same. The distance that Malik covered was 8 plus 3. All right? The distance that Malik covered, I'm going to write it out because a lot of people use D for both distance and displacement. The distance that Malik covered was 11.0 meters. Malik's displacement was 8.5 meters, comma. It wasn't west, it was near, right? 69 degrees south of west. All right? 69 degrees south of west. This is a popular convention where you first say either north or south and then of either east or west in this position. There's lots of different ways that you could do it. All right? This is one convention that's fairly popular. All right, so for distance, we have just the magnitude of the distance. For displacement, you have to state both a magnitude and a direction. In this case, the direction is an angle. If the direction were exactly east or exactly north or exactly south, then you would just say that. If the direction were 45 degrees, you could say northwest or southeast. All right, the only time you can say northwest or southeast or northeast or southwest is when it's exactly a 45 degree angle. This is not, this is a 69 degree angle. All right, now, if the question read, calculate the magnitude of Malik's displacement, then you would not have to calculate the direction. If they only wanted his magnitude, you would use Pythagorean theorem and get only the magnitude. They're not asking for that angle. It's quite common for them not to ask for the angle. All right? In other words, what is the magnitude of Malik's displacement? Okay? But if they ask for the displacement, you need the magnitude and the direction. In this case, the direction is the angle.